Welcome back to ECE 501B. Your passport is due on the 27th, and that's not your official passport. Someone asked me in office hours today, do you want my official passport? No, I'm not stamping a passport or anything. This is made up for this class, and it's to allow me to get to know you a little bit better. Homework number 1, I believe I've now made that available on D2L, and that's due on the 5th. That's in a couple of weeks. That's on a Wednesday. I thought about making it due on Labor Day, and I thought, well, that's Labor Day. So it's due on the Wednesday. And again, those are due in the Dropbox as a PDF, a whole PDF, not pages of PDF, just combine. Hopefully you can combine them all into one file to make it easier for us to access. And just drop those in the homework number 1 folder in the assignments page of D2L. Today what I want to do is pick up where we left off, which was talking about vector spaces, and now I want you to think about things that are more than just these tall, thin columns of numbers that we usually think of as vectors. And I'll provide you with 13 examples. I'm not superstitious, so 13 shouldn't, I hope it doesn't bother anyone else, but it just happened that there are 13 examples that I've selected. Then we will simply state some of the properties of vector spaces, and the notation is Proposition 125 through 131, the different properties of vector spaces that are encompassed by those numbers. Then we will quickly go through some different types of proofs, not going through the details, but just sort of giving you a rough idea behind how you can maybe prove a theorem. Then we will actually use that to prove Proposition 126, which is one of the propositions we'll just state earlier, and we'll illustrate that proof by contradiction. We won't do a direct proof, we'll prove it by contradiction using one of the strategies of proving. Then we will look at subspaces. So in a very general sense, those are subsets of the big vector space, but those subsets have to be more than just a subset. They actually have to be or satisfy the properties of a vector space in order to be a subspace. So there's a difference between subsets and subspace, but conceptually they're kind of the same, but you need the subsets to also enjoy all the properties of a vector space. And then we'll talk about how we can combine those. Now that we have subspaces, we've started to pull apart bigger vector spaces and identify subspaces. How can we combine those? And what are some strategies? There's vector space sums, and then there's a different kind of vector space sum, which is called a direct sum. So in very general terms, this direct sum means, well, maybe I shouldn't say in general because I may make it more fuzzy. So let's just wait until we get there. But the direct sum is a particular way to subdivide a vector space that's a little bit, it has uniqueness properties in terms of the vectors that you can build from these subspaces versus just a generic vector space sum. Here's a recap. A vector space is sort of 3 concepts. It's a set of vectors, and then those vectors enjoy 2 or possess, or this vector space possesses 2 binary operations. A vector addition, so each of the objects that are coming from a vector space, those are 2 vectors, you can add those together, and scalar multiplication. You can take a scalar from your field, your underlying field of numbers, and use that to scale any object from your vector space, and that scaled vector belongs to the vector space. Here are some examples of those, and I'm calling it VS1 through, and you already know where we're stopping, so we will see about that. We'll start with maybe the obvious vector space. V is equal to the real line. So here is just R being the real number line. That real number line actually forms a vector space, which is what I'm denoting capital V. So if I could make that any better, it would be a bold maybe V to mean this is a vector space, and it's all of the real line. And now that I've given you sort of this default, let me try to suggest that you keep something else in mind as you're thinking about vector space. This is a disclaimer. Remember, to actually think of a vector space, like a collection, so here it is in sort of quotes, a collection in which any linear combination makes sense. And a linear combination is adding pieces together, scaling those pieces. That's a linear combination. A collection that makes sense, and not just or not like a collection of columns of reals. That's what we typically think of when we are doing a linear algebra class. We have a vector of real numbers, and that's what we use to create our vector spaces in that class. But I'm trying to let us think about other generalized versions of vector spaces, although, so now I'm giving you sort of a caveat within a caveat, or a disclaimer within a disclaimer by this word although. Sometimes it can be helpful to actually keep these columns in mind. So sometimes it's a fallback. If you want an example or you're thinking about something, you may go, well, let me just see if it works for the traditional linear column or column of real numbers. So although it can be helpful to keep these columns of real numbers in mind. So I gave you a disclaimer, and then I put a disclaimer on the disclaimer. Oh well, that's trying to get us thinking many different ways in this class. I've introduced one vector space. We have a few more to go. VS2, vector space example number 2. A vector space V is now what I just said to forget, or not forget, to not focus on. V is equal to R to the n, where r to the n is some n-dimensional vector, and each of the Nevada coordinates in that vector are real numbers. So an n-dimensional vector with elements in R. Was this the class that I asked about your free time? I'm guessing maybe some of you might like to read. Has anyone read Flatland? It was recently released. Just teasing. It was written in 1885. But it sort of goes back to the Victorian English era. And it has different sort of, you would read it as sort of a math thing, but it has sort of hidden meaning, maybe, if you really read into it. So it's called Flatland, A Romance of Many Dimensions. But it's trying to get you to think beyond a two-dimensional or three-dimensional vision. So it's trying to help you better understand multi-dimensions, which r to the n, if we have 10-dimensional space, you're going, how do I wrap my head around that? Well, maybe Flatland, I'm not going to go through the entire, the complete title is A Romance of Many Dimensions. It was written by, I think he actually had Abbott twice in his name. It's something Abbott, but I'm just going to use one of those, in 1885. And it's kind of interesting to read the history. Not that I've done that, so there's a disclaimer. But you can access this through the U of A library. There's many different versions. There's actually an annotated version of that would help you maybe decipher from one person's perspective what he was trying to infer or talk about in Flatland. So one way to think about that maybe is you have a rope, and on that rope is an ant. That ant maybe sees a two-dimensional surface, but it's sort of on this three-dimensional if it starts walking around. Just a way to think about, how do I get my head around two dimensions in a three-dimensional? All right, Flatland. Let's move on. CS3. Where did that notation come from? I was so worried about multiple dimensions, I pulled a different letter out of the hat. It's supposed to be what? VS, vector space, keep me sane, vector space number 3. And this is really just an extension of what we just talked about. Instead of R3, now we have, R to the n, now we have C to the n. Now each of these entries in this n-dimensional vector are complex numbers. So we've really just sort of doubled the dimension in a sense. So here is an n-dimensional vector with n element, or with, let me just say, with elements being complex. Vector space number 4. Suppose V is now M sub Mn. So it's Michigan by Nevada, a matrix, where each of these entries in that matrix are complex. We now have a complex matrix that's m rows tall by n rows wide. And that could be a vector space. This is now an m by n set of matrices where each of the entries in that matrix can be a complex number. And that's a vector space. And instead of calling them matrices, now each of those is a vector. That matrix is a vector in our vector space. That's this sort of abstract way of using the word vector. So all of these objects in the vector space are vectors. We can call these matrices vectors. Since the matrices are elements or objects of the vector space. That was example 4 of a vector space, matrices, where each matrix is a vector. Vector space 5 example, the vector space now is C raised to the infinity. What in the world is that? Well, here we're saying that that's a vector z that has elements or coordinates z sub 1, z sub 2, z sub 3, and it just keeps going. It's an infinitely long vector. Maybe it. Where each of these z sub I are complex. And what we want to get comfortable with is combining these. We'll learn ways to check whether a vector, if something is a vector space, and we'll really be able to check sort of 3 different conditions. Is the 0 vector, does it belong to that? Is that particular proposed vector space, is it closed under addition? Is it closed under scalar multiplication? And you, I hope, can see how you can combine with vector addition vectors that belong to this vector space. They just component-wise addition again. That's vector space number 5. So in a sense, there's an infinite dimensional vector space. Another infinite dimensional vector space number 6, V is now C square bracket T, where T is now defining a closed interval. Capital T is little t between endpoints A and B. Or you might see this written as V is equal to C square bracket, open square bracket, A comma B, close square bracket, where C now represents the set of continuous functions on this closed interval between A and B. This vector space then is the set of continuous real valued functions defined over the real closed interval a comma b. And that's infinite dimensional. But now you pick one of those objects, a vector, you pick another vector from that set, you can add them, you can scalar multiply them, and you can have the 0 vector. It's identically 0 between A and B. And you have all the other properties of a vector space satisfied by that example, example 6. Vector space 7. We can generalize that. Now we can just say functions on the real, defined over the real line. So now our vector space V is the set of functions f such that f of x, sort of the image of that function, is a real number when the argument or the domain is a real number. So you give that function a real number as an input and it spits out a real number output. And it's over the entire real line. Or we could maybe shorten that in terms of its notation. We could say the set of functions f such that R maps to R. Another maybe more condensed way of writing that, where this is now the set of real valued functions f defined on the entire real line. Where G and F are both in this vector space. Question?
For vector space 6, does it also have additive inverse?
So now is vector space 6, does it have an additive inverse? If you have a function that's continuous, the set of continuous real valued functions defined over the real line, over this closed interval, is there an additive inverse? You give me a function, I'll just scale it by -1. And then I'll add those two together. Isn't that the additive inverse? So I think that should sort of verify that in fact this does contain additive inverses. And that same approach could be used here if somebody said, well, what's the additive inverse of f of x? Well, now you just put a mirror down on the x-axis and mirror it across, and you say, oh, just add these two together and you'll get the 0 vector. Does that help? I'm not sure I repeated the question, but I'm wanting to make sure that I repeat your question so that the people online, well, they're not online. They're that ant walking on the line, tightrope. No, so they are, and I apologize for those of you that are trying to listen to this and wondering what I'm doing. But maybe you heard a little laughter. It maybe had some impact on the class, but for those of you listening at home, now I forgot where I was going with that. But you could now draw that picture below or just the mirror image to produce, because we could have these F's or G's being both positive and negative over the length of X. Right now, it looks like I've kept them always with a positive image, but they wouldn't have to be. Here, I'm assuming, or I'm saying that G, just because in the curly brackets for the definition, I said F, well, G is there, H is there, whatever I wanted to define, as long as I say G is an element of the vector space V. Likewise, F is also an element of the vector space. Where are we? 7. Need to learn how to count. We have a few more, don't we? So now let's do vector space example 8. Suppose the vector space V is now C to the N bracket A comma B. Do you recognize what that is? The notation. If I just said C bracket AB, we've already defined that. Now I'm introducing an exponent, but by that exponent I'm meaning how many times those functions are differentiable and still remaining continuous. So these are functions that are differentiated n up to n times, and they remain continuous functions over this closed interval from A to B. Let me see if I can write that. This is the set of all real valued functions f for which f, the first derivative of f, with respect to its argument, which is the real number line x, f double prime, my people. Like I said, new technology. I have no idea how these people are now getting into my lecture. But go away, please, for now. I'm impressed that I have that many people that are interested. I have no idea why it jumped there, but maybe probably because it got nervous when I started talking about derivatives. Everybody does, all the people do usually. So now we're differentiating n times. Those derivatives exist and are continuous on the closed interval A comma B. Those are infinite dimensional vector spaces. Let's look at some more. So we kind of shift gears a little bit. Here's vector space example 9, which I'm now saying is the set of all polynomials. That's a vector space. Notation, if I can, it's some script P over the field F. And what does that mean? I'm pulling my numbers for the arguments here from F. What's F? Real or complex. So either one you could decide, but here I'm going to say a sub 0 plus a1z plus a sub 2 z squared, and that just keeps going. This is the set of all polynomials such that these coefficients a sub 0, a sub 1, a sub 2, those all are coming from the field that we've selected, either real or complex numbers, and z. If we plug in the appropriate a's and we evaluate at a given z, a real number or complex depending on what our field is, that's now what that polynomial evaluates to. But all of these, or the set of all polynomials, forms a vector space. Because you can add those up, you can scale those, you have an additive identity, etc. for these polynomials. Vector space example 10. Now we could just go crazy. I could have had 100 vector spaces if you buy that first one being a vector space, being all polynomials. What if I now start specializing those and say, oh, the set of second order polynomials, set of third order polynomials. You see how we could just be here all night, everybody bring a little snack? Nobody like that idea? Oh boy. So here, this is, we'll stop with this next one, with this process. This is now the set of second order polynomials over the real numbers. And I think you can see that you could now take this into complex numbers too, if you wanted to, and now double your possibilities. But this would be, let's say, script p sub 2 r. So there I'm sort of using this to illustrate or define the notation that we might use in this class. If I say script sub 2, or script p sub 2 over r, then you know that we're talking about the set of polynomials that are second order with the coefficients real and evaluating over the real numbers for the arguments. So this is actually a vector space, but you could view it as a subspace of the one before, vector space 9. But here is a sub 0 plus a sub 1z plus a sub 2 z squared, such that a sub 0, a1, a2 are real, and z is also real. Sometimes, though, it helps, you know, I had the disclaimer on the disclaimer. This we could sort of think about the same way as we could think about a 3 vector. Because this, if you give me a 3 vector and I associate the first element with a sub 0, the second element with a sub 1, and the third element with a sub 2, you now could hand me a polynomial, a second order polynomial, if I just hand you a vector, a 3 vector. So if you wanted to think about this problem maybe in a different way, you can say, oh, I can think about what I'm dealing with script p sub 2 of r like R3, where we now have p of x is equal to a sub 0 plus a1x plus a sub 2x squared. And this now you could think of by saying, oh, that's really sort of like or corresponds to a sub 0, a1, a2, this column of reals that has 3 coordinates, those are consistent. You could say, oh, you give me a 3 vector, that's like me talking about a second order polynomial. Again, we're trying to open up or be capable of thinking abstractly with these ideas. Vector space example number 11. Here, let's look at or talk about a vector space of 2 by 2 matrices. So that now maybe we have an M sub 2 by 2 is the set that we're talking about, or we could say, oh, that's the set of A, B, C, D, such that those 4 elements in that 2 by 2 matrix are real. And now do you have a way of thinking about this similarly to what we just did for our second order polynomial? Now, if we're talking 2 by 2 matrices, you could also say, well, that's like a 4 vector. Just give me A, B, C, D stacked as a vector. And I can think about it maybe in that sense if I wanted to. And you could have MATLAB do that. You could, what? Just stack BD underneath AC if you wanted to in MATLAB, and now you can play with vectors instead of worrying about matrices. So here, this arrow, which I'm using to denote corresponds to or the same as, R4, such that A, B, C, D, now I'm stacking them differently. I'm sort of putting them in a row and then transposing that row, but you can put them in there however you want as long as you're consistent. There is now R4. Probably didn't know there could be so many different vector spaces, did you? But I already told you I'm going to give you 13 examples. Where were we? 11? So let's go to 12. Now you can go home tonight and just start creating all sorts of vector spaces. Maybe you don't want to tell anyone you're doing that, but they might look at you a little odd. Oh, I'm going home and going to create some vector spaces. Oh well, they know what we are, right? Engineers. So here, vector space 12. Let's say that this is now a set of functions f where n maps to r. Can you decode what that is? What's f? A function. I could maybe even answer that. What's n with that vertical line in it? What am I? Did I define that the last time? No. So now I'm having you speculate, but what do you think that is? Natural numbers. So here we have arguments. That's our argument of these functions. It will be the natural numbers. And the image or the output will be the reals. Let's just get our minds around this and look at some examples. for example, suppose we let, and I'm going to subscript these just so that we can kind of keep track of them. Let's say our first example, f sub 1 of n, is, let's just say it's n plus 1. That's an element of V. Suppose we let f sub 2 of n equal 2n squared minus n. Is that a member of this vector space, or an object, or a vector in our vector space? Sure. We're only saying the arguments are n, so we can evaluate this on any natural number. So that's what happens if we were to add those two. Will the sum of f1 and f2 be in V? We said it's a vector space, so it has to be by that definition. But yes, it is. If we now said, oh, let's just call f of n equal an algebraic sum or a linear combination, and I'm not going to even scale those. I'm just going to say f1 plus f sub 2. Now we have n plus 1 plus 2n squared minus n and that's also in the vector space. Since it's a vector space, it has to be closed under addition. So however we linearly combine any of these vectors in the underlying vector space, we have to be able to get the result ending up in the vector space. Or if you wanted to see sort of, or think about that another way, you could say, let's just chart this out. What happens when we now plug 0 in for f of n? See, you could go home and do this tonight, right? Another exercise. So where are we at now with 1? 3, 2, whoops, I'm covered up. Is that 9, and then 3, 4. So we had 16 times 2, or 32 plus 1. So this now, you could say, oh, f really corresponds to, you plug in an n, and it will produce this infinite column of numbers. 1, 3, 9, 19, 33, on down. So you could say, oh, now I have an infinite dimensional vector space. Vector space example number 12. And you could think of it as f of n is 2n squared plus 1, or you could produce that vector and say, oh, it's this as well. Instead of the functional form, it's this infinite vector. What are some other examples of vectors in that vector space? Let me write some down and you can say yes or no. Suppose it was 2.7n. That's approximately what? What's 2.7 approximating? Isn't that E? So now we have En. Not really, but 2.7n, that's okay. What about f sub 4 of n? We just need the argument to have n in it, and we can evaluate, replace n with any of the natural numbers, and the result needs to be a real number. That's okay. So now we could say n over pi plus 2. I don't know where these are coming from. Don't ask. I just cooked them up. Shouldn't have said cook. Now I'm hungry. F sub 5. since somebody mentioned e, how about e to the n? That's okay too, isn't it? Are you just about tired of these? That's why I stopped at 13. So we have one more, 13, as an example for a vector space. Let's say it's W. Why I switched to W instead of V, I have no idea. But now let's say W is the set of functions f such that R is taken to R. We're comfortable with that, such that the second derivative of f with respect to x plus f yields 0. Can you think of an example there? So if you're thinking trig, you're thinking in the right, in one example, you could say, oh, f of x equal a cosine x plus b sine x. That would be a particular vector in that vector space. You could also sort of say that, oh, then if you just give me that structure, if I know A is going to scale cosine of x and B is going to scale sine of x, then really all we would need to keep track of is, if you give me an x and A and B, I can give you the same answer. So this corresponds to where we're now assuming these coefficients are real. So this is R2. Questions on those examples, but you might just keep those in your hip pocket. When we're talking about vector spaces and we're just doing something in an abstract sense, you might say, oh, let me see if, what was one of the examples, and play with it and see if it is interesting based on what we start doing with vector spaces. It doesn't have to be limited to a tall, thin column of real numbers. Yes?
In kind of these different examples, does a vector space always have to have 0 in it, especially when it's like a bounded example or when we're talking about functions? Does it always have to have 0 between those?
So now the question was, does the vector space always have to have 0 in it? And the answer is, based on last time, didn't we say that it had to have a 0 and a 1? So it has to have a 0 vector. Whatever that 0 vector means is going to obviously depend on the vector space.
So then like one of the bounded examples, like between A and B, it just implied that 0, A is less than 0 and B is above 0 or something like that.
Oh, so in the one where it was a continuous function between A and B, now you give me an A, a B, it could be anywhere, let's say 1 to 7, but now the 0 vector is what? The identical 0 function between those two limits. So the 0 is the image on those sort of arguments. Or the arguments are giving you the domain over which your range or image is being generated, and the image or range needs to be 0 in terms of a function or in terms of a vector. But you have to have a 0 vector, and what that vector means depends on the vector space. Does that help? So let's now talk about, or really just sort of present, some properties of vector spaces, and it's actually sort of now playing into that last question, some of these properties. So properties of vector spaces. And if you're reading along or wanting to know where these are coming from, or you want to read up on those, which you should be, you can find these on pages 15 through 17 in the book, Axler. Property 125, or entry 25 in chapter 1. This is a unique additive identity. Does that sound familiar? There's our zero vector. So property 1.25 says we have a zero vector. There's a unique additive identity. The additive identity means you add it to any vector in your vector space and you get the original vector back. So V, the vector space, has a unique additive identity. We have a zero element, where A is actually key in that description. A unique zero element. 126, we have a unique additive inverse. Or every element in V, and this gets back to an earlier question about, is there a additive inverse? Every element in V has a unique additive inverse. He obviously used some other equations to label or to use some of the numbers. Now we're jumping from 26 to 29, but we may probably be catching all of the properties of vector spaces. In this one, we have 0v is equal to 0 for all vectors v in the vector space, or for any v in the vector space v. And here, are those zeros the same? Well, they look about the same, but you can't draw very well. What's the zero on the left? That's a scalar. What's the zero on the right? A vector. So these aren't the same, although they look object-wise about the same, but this is a scalar, and there's a vector. So we're overusing zero. Question?
Do you have an example where the additive inverse is not unique?
So now, is there an additive inverse that's not unique? No, we're going to show, actually, let's see, are we doing, actually, I think we're doing the proof of 125. We're showing that the additive identity, I don't know, I'm getting ahead of myself. So we will show that the additive inverse is indeed unique if we can find a vector that when added to the other vector gives us 0. We can't find another vector in the vector space that's different from that, if that makes any sense. So you give me a vector, I'll give you its additive inverse, and someone else in the room, if they hand you an additive inverse, our two additive inverses are going to be the same. We can't give two not different vectors that when added to the vector that we were given gives us the 0 vector. Okay? That's just the property of vector spaces. We want it to be unique. So here I was just, this one is, 29 is playing on the two different ways of viewing 0. 30 is A0 is equal to 0 for any A in our field. A is a scalar. Is 0 like in 29? On one side it's one thing, on the other side of the equality it's another. No, here it's a vector on both sides. So you have to be able to look at the expression and infer what 0 corresponds to in the appropriate example. (131) minus 1v is equal to minus v for every v is an element of v. There's our additive inverse. And it's unique. You give me a v, I'm just going to negate it and hand it back to you for the additive inverse. I'm going to scale it by minus 1. So those are some properties of vector spaces. You now have a collection of vector spaces to be drawing from, to think about. Let's now look at how we might prove different true statements, different theorems for these concepts. Some proof techniques. And here we might have a general structure. And for now, I'm just going to assume this general structure is of a conditional form. So there's other ways of thinking about a structure, but let's just concentrate for now of a conditional form. Or the true statements, the theorems that we will look at, really have one statement yields a second statement. That will be our theorem. Or you could think of having a hypothesis, a true statement, yields a conclusion. Or A, with this arrow, implies B. The same way of thinking, or different ways of inferring the same thing. A implies B. Or we have an antecedent leading to a consequent. Or we have if A, then B. And that's maybe the more standard way of thinking about a conditional statement. If A, then B. If A is true, then B. That will be our true statement, or that will be our theorem. And we now want to know what are some different strategies, what are some different techniques that we can prove this theorem or this statement is in fact true. proof techniques. The one, or the first one, is what we could refer to as a direct proof, where we simply start with the first statement, start with statement A, we start with A, and we progress via steps to show logically that B results or B falls out. So we start with A and progress to showing B is true. Now, in doing this, you can do this in secret. You can go somewhere away and you can say, well, I just need to eventually show that A logically produces B. But in the process of building that, you might scratch around a little bit and say, let me start with B. I need to start with A. I need to show B. And you might start working from both ends and see if you can meet in the middle. So if I need to get B, what's sort of the first thing above B that maybe I could show, and then I can immediately drop down to B. And if I'm starting with A, what's my first step to show to maybe get me towards B? If that makes any sense. So you might work from the ends and try to get to the center. And then at the end you can say, it's obvious, go from A to B. When in fact it may be you probably didn't derive it that way initially. But we need to start learning how to read and also write proofs. And that's one strategy of doing it. The direct approach, A logically to B. So here you may want to work from ends AB, or you might see this referred to as the forward-backward strategy. And that's in the book by Solow that is one of the books for this class. So a direct proof. A second proof strategy is a proof by contradiction. Here, again, we start with the first part, the first piece, the hypothesis. We start with A, but now we do a little bit of a twist. We assume not B. So now we start with A and assume not our result. And we try to derive a contradiction or a false statement. So start with A and assume not B and try to derive a contradiction or a false statement. That's a second strategy for proofs. We don't always have to do the direct approach. Another third way is what's called the contrapositive strategy, which you may actually want to try this before you use the contradiction. Usually you maybe start with the direct approach. I'm not getting anywhere. We'll try the contrapositive next, then the contradiction. So maybe I should have reordered these. But the contrapositive is really a conditional argument, but you start with not B, and that should imply not A. And if you can show that, then you're done. So here you have not B implying not A. So here, in the contrapositive strategy for proving, you assume not B, and you progress to show logically that that leads to not A. And you don't even have to go back as far as your 2-year-old hat. You're probably thinking, why? I'm a little older than 2 and I'm still asking why. Where does this come from? Well, the 2 are logically equivalent. And we can show that by looking at the truth table of A implies B and the truth table for not B implies not A. And we'll end up with the truth tables being the same. Let's just show that for completeness. So now we're trying to figure out why. And if we want to show that they're logically equivalent, we can do that with a truth table. So now this truth table, let's say I have A and I have B. And now we just need to build up the possible combinations. We could be true with A to generate a true B. We could have a true A and a false B. And now we could have false and false for A, and that should be true and false for B. We want to look at all the combinations of A and B, and that should do it. So now the next column in the table is going to be the conditional A implies B. So here is if A, then B. This is our conditional. And what does that look like? I like to sort of think of this as, when are you going to catch somebody in a lie? So if I said something like, if it rains today, then I'll go to the movies. So what's A? A is the hypothesis. If it rains today, then if I'm not lying, I'm going to go to the movies. Right? So if A is true and B is true, then A implies B is true. If A is true, if it rains, and I don't go to the movies, I've lied, haven't I? So it's false. What if it doesn't rain? What if the hypothesis is false? It was sunny. Then what? And B is true, it's true. What if it's false and I don't go to the movies? Still doesn't matter, it's true. Is that okay? I'm not caught in a lie if it doesn't rain. Is that clear? So that's the truth table for the conditional. If A, then B. So now let's fill out the other piece of that and show the equivalence, the logical equivalence of the not B implies not A. So we need a not B and we need a not A. So now let's negate B. So we just go false, true, according to B's column. And now we just negate the A column. So now we're false, false, true, true. And this column here is going to be not B implies not A. So using the same logic before, if we start with a false hypothesis, what do we conclude? True, right? Irrespective of what the result is. So there are some trues. What about the last row? True implies true. That's true. When we get caught in the lie is when the first hypothesis implies a false. So here's a false. And what we're wanting to do is compare this column with that column. And we're hoping that they're the same. And they are. They're logically equivalent. So I hope that I've demonstrated in this that, okay, if I show not B implies not A, I've really just shown A implies B by a contrapositive argument. And what I was using to sort of talk about the conditional was I maybe said A, my hypothesis was if it rains, and maybe I should qualify that today. So I guess I need to go to the movies tonight, huh? That ain't happening, so I'm going to lie. I haven't gone to the movies in, you don't even want to know. Probably you weren't even born yet. Are you kidding? So don't model me, okay? If you want to enjoy life. Let's move on. B is, I shouldn't have used this example, huh? B, I will go to the movies. All right, let's move on. That contrapositive's getting kind of... Are we clear on that? So another one might be for proving the process of induction. Here, to prove something by induction, you essentially prove the base case, where the base case might be n equals 0, n equal 1, or it's some starting value of little n. So we prove the base case. And that might be n equals 0 or n equal 1. Then we use the induction hypothesis. We assume that it's true for the nth case, and then we have to show that it's true for the n plus 1 case, assuming it's true for the nth case. We assume true for n, and this is what's called the induction hypothesis. And we show that it's true for the n plus 1 case, assuming or using that it's true for n. Questions on proof techniques? No one's yet fallen asleep. They want to know how many more movies I haven't seen, huh? Well, I'll keep you awake, maybe, thinking that way. All right, so let's look at the proof of proposition 26 in chapter 1. And we're going to use the strategy of contradiction. And proposition 126, maybe I won't write it here just to save time, but that's every element in V has a unique additive inverse. So what's the contradiction strategy? What do I assume? Let me go back to 126 before I rewrite it. Hopefully I have it somewhere. Every element in V has a unique additive inverse. So what's the A? What? Every element in V. And B has a unique additive inverse. So what I'll probably do is offline, I will maybe show this and provide you with the video if I decide I'm going to video it. Okay? But you can go home and try to do that. So now what you're trying to do is show that you come up with a contradiction. That basically if you've assumed W and W prime are additive inverses, can you now show that those two have to be equal when maybe initially you assumed they were different? We'll pick up at that point or somewhere beyond that, depending on what I decide to do between now and Monday when we meet again.